week we had an example 6.2, and what we did is we tried to calculate the current and also was designing the resistance RE based on the given conditions. So remember, what was given was VB is 0.7 volts, current is 1 milliamps. Now, if your current is 2 milliamps, VB actually changes a little bit, slightly. And the change is based on the equation of IC equal to IS times e to the power VB over VT. So you can see here, so IC and VB, basically, they're related in that exceptional relationship. So based on here, we found that the actual RE is 7.07 kilo ohms is what we need if we consider the actual device physics. If we don't do that, if we assume simply saying VB is 0.7, it doesn't change. When the current changes, we got the resistance to be 7.15. So there's a slight difference between the two if you consider VB as a constant or you consider VB as a variable based on IC. So in that case, let's move on. We're going to look a few more examples today, and then we will move on to, because this chapter, again, similar to the last chapter, there's just a lot of different variations how to solve each problem. So let's say we have this problem says that the voltage VBE was given 0.7 and beta is 50. So they want us to find IE, IB, IC, and VC. So that's the given condition. Let's get started. So VBE. So VBE is 0.7, which means, so VBE is 0.7. So let's start from here. So if VB is 0.7, because VB in this circuit, the base is grounded. So therefore, VE would be lower than the base, so it's lower than ground. So how much do you think VE is going to be? So it should be minus 0.7 volts. So oops. So that's easy to get. And then if we know VE now, we know RE is given. So we should be able to easily find IE. So that should be a fairly easy step to do. So IE will be VE minus, let's call VEE divided by RE. And in this case, you have VE is minus 0.7 minus the VE is minus 10 divided by RE is 10. So we have here IE equal to 0.93. So, and then the next step is we can start to find alpha because beta is given. So no, alpha is beta over beta plus 1. So that gives you 50 over 50 plus 1 gives you roughly 0.98, I believe. Yeah. And then the next step is we can find IC because IC is alpha times IE. That's too big. And equal to 0.93 times 0.98. That gives you 0.91 milliamps. And then the next step is to find IB because we know IB is equal to IC over beta, right? So IC is beta times IB, so that's a very straightforward expression. So we've got that equal to 0.02 milliamps. And alternatively, you can also say IB equal to IC minus IE minus IC. That's the same thing. You can do that as well. So we got all the currents. So from here, we can also, I would say, we'll just do a couple steps further. So now we have we found IB, IC, IE. We have found all those. We did use the 0.7 and also beta. So we use all those parameters. The only thing we have not found is VC. So we can find VC. The importance to find VC is to make sure that this is in saturation. So VC is VCC minus IC times RC. VCC is 10. So IC is 0.91 times RC is 5K. So that gives you 5.45 volts. Now, the reason I want to calculate VC is also that I want to see how much VC is going to be. So VC is VC minus VE. So that gives you 5.45 minus 0.7, right? So that gives you 6.15 volts. Apparently, this is important because we know that now VCE is larger than the saturation voltage. If at the end, like in the next couple of examples we're going to find, if you find VC is less than 0.2 or 0.3, or sometimes actually VC becomes negative, which means all this calculation was wrong. Because what we're doing here, we assume it is in the active mode, in the linear mode. But in order to be in linear mode, VCE has to be larger than 0.3. Okay. Now, if it's less than 0.3, you're wrong. You have to go back saying, oh, my assumption is wrong. I need to redo it. How do you redo it? Well, now you assume it's in saturation. You redo the problem. Now, of course, for this particular problem, it is in saturation. So, it is inactive, so we don't have to redo it. We'll see some other problem. We're going to see that we have to redo them. Okay. So let's move on to the next example. So in this example, what it tells is that in circuit, VB is, okay. So VB is 1 volt, that is given. And VE is, okay, so this is this is PNP, right? So now we're using VEB instead of VBE. So VE is now higher. So VE is 1.7. So therefore, this circuit got to be conducting, however, it could be in saturation or it could be active. So most of the time we will assume it's active and then we start it, right? So, and then I want to ask you what are better for this transistor and what voltage VC do you expect a collector? So we want to find VC over here. So since we know VE, the VE is given and the resistance is given, so it's easier for us to find IE. Okay, so we will see step number 1. So IE will be that 10 volts minus 1.7 divided by 5K. So that gives you VB active mode, or say I use 5K 1.66 milliamps. Now I verbally said, but I didn't actually do it, is because VE is 0.7, VE is 1.7, and VB is 1, so the difference is 0.7, which means this transistor actually is either active or saturation, right? So it's conductive, so we don't have to, in reality, you might have to verify that. Okay, so now we have VE. We found VE, we found IE. So we need to assume. Now, I want to assume it's in active. Now, again, we make this assumption later on, we have to verify. So we're assuming active now means it means that we can find what happened? Oh. Okay. We can find either IC or IB. IB is IE over 1 plus beta. that equal to 0.01 milliamps, and IC equal to IE minus IB, or it can say beta times IE, but I mean alpha times IE, or beta times IB, but we don't know beta, so that's why we couldn't use that equation. Yeah, go ahead.
How do we know it's 1.001 milliamps? Don't know beta.
IB, you're right. Okay. You're absolutely right. We cannot do that because we don't know beta. We need to find beta. Well, okay, so here we can find IB from the circuit, the current going this way. If you look at the circuit, you see there's going to be IB that goes down with a VB over 100K. So VB is 1 over 100, so that's 0.01 milliamps. Okay. Thanks for reminding me. So here, because VB is given, so there's current flowing through the 100K resistance. And that current actually, because this side is not connected to anything, you see that current is actually flowing out of the base. So that is IB. So this current is same as IB. So we found IB to be 0.01 milliamps. So now we can do is we can do well, we know that IB is good, IC equal to IE minus IB. So that's going to be 1.65 milliamps. So therefore, or beta equal to IC over IB, it's going to be 165. Now, of course, from here, you can say alpha is beta over beta plus 1. That's going to be 165 plus 165 plus 1. That gives you 0.994. And the last step is we need to find a VC. The VE was given. If we find once we find a VC, we have to verify that VEC is more than 0.3 because we are show missing active. So that's the last step we need to do. Now we already know VC. We already know IC. We already know IC. So VC is going to be the negative 10 volts plus the 5K resistance at the bottom times IC. So it's going to be minus 10 plus 5K times IC is 1.65. That gives you minus 1.75 volts. So the last step is to find VEC. Now remember, this is a PNP. So we find VEC instead of VCE. So VEC is VE minus VC. There is VE is 1.7 minus 1.75. That gives you 3.45. That is larger than, let's say, 0.3 volts. So this is in. So it is in saturation. So that's the last step that we need to verify. Now, if the last step that you found VEC is less than 0.3, we need to go back to redo the problem, assume it's actually not in active mode, and it will be doing in saturation. For this circuit and the previous circuit, it's not going to be in cutoff because we know, for example, this one, we know VEB is 0.7, so it is not going to be in cutoff. So you can basically ignore that method. In the previous problem, we have also, like in this problem, the circuit will never be in cutoff. Why? Because assume it's in cutoff, there'll be no current. If there's no current, means the voltage over here is going to be minus 10, right? So now from base to emitter, you get 10 volts difference. That's impossible. So therefore, this will not be cut off. So some of the circuit, right away, you can see whether it's cut off or not, but some of them may not be that straightforward. So we can also remember earlier we draw that IC as a function of VBE in other way. Let me see. So what we have been doing is we use this more than the other graph. Is we draw this as we see, right? So we have this one here, and each of this one is corresponding to VBE. And then if you interpolate from this graph, you can find the relation between IC and VBE. So you guys probably remember this, look familiar. This is what we get for diodes. So this basically, so if you look at it, this is like ID and this is like VD. So when it reaches 0.7 volts, it shoots up dramatically. Because it's an exponential relationship, so by the time it reaches 0.7, so the current actually goes pretty vertical. There's very little change in VB resulting in a very big change in IC. So this is just another way to express our current voltage relationship. And I can just remind you of how the p-n junction of diode works this way. But that actually happens. That happens for a given temperature. If temperature changes, this curve actually shifts. When temperature increases, this actually goes like moving. It's moving this way. So suppose you're at 25 degrees C, you're here, but when you increase temperature, actually, this voltage drop reduces. So that is important because when we design electronic circuit, we have to consider the two temperatures. One is the ambient temperature, the environment temperature. The other one is actually the device temperature, right? So for example, if you're using your phone here, the room temperature may be, say, 22 degrees. But as you use it, the chip temperature goes up. Or when you charge your battery, it goes up. When it goes up, the whole thing actually changes. And the direct representation is the junction, the junction voltage. For the same junction voltage, the corresponding current will change. Right? So that is impact a lot of applications. Like if you go to, say, satellite, you can go to negative, say, 100 some degrees C. Or if you go to Arizona, you're sitting, like if you leave your phone outside in the summer, it can go to 50 degrees C, 60 degrees C. A huge change. And you might see your phone slow down, your computer slow down, things like that. And the reason that we have to tackle, we have to deal with that temperature change. But of course, here, what you see directly is the current changes with temperature. And that is reflected, in fact, at VT. Remember that VT, 25 millivolts? Usually that's 25 degrees C, but when temperature changes, that value actually changes. Okay? So basically, you write down that expression is IC equal to IS e to the power VB over VT. So that VT changes with temperature. So as temperature increase, as temperature increase, your VT will actually decrease. Yeah, and then your current IC actually increase. And then I think to understand this is to think about when temperature is higher, it's easier for electrons to move. So therefore, the resistance, the voltage needed to move the electrons is less. So that's how to understand this phenomenon. Okay. However, even though you look at this curve that we drew before, up to this point, we make it flat. What we are saying is that when VB is given, whatever VCE is changing, this IC is constant. Now, in fact, when you do actual measurement of a device, that's not the case. So what happens is when VC increases for a given VBE, let's just take one curve, like the bottom curve over here. As VC increases, that current actually increases a little bit. And that is a slope. So initially, what we were saying is that, like this one here, it's going to be like constant. Actually, it is not constant. It's not constant. So this change between this delta between the actual voltage is blue and the ideal voltage is red line, that delta is related to a parameter called early voltage, VA. So it's interesting because after you do the measurement, you find that for given VBE, you extend the slope all the way to across this point, you get a value, which because this vertical line, this horizontal line, this horizontal x is a voltage, right? Because we see it, right? So this value is a voltage. So we call it VA. The interesting phenomenon is that as you increase VBE, which means your current is going to increase, right? So you increase VBE, your current increase. And you extend this same line down, they will cross at the same point. So as you increase VBE, you can see that line becomes more and more slanted, which means the difference between actual current and ideal current is going to become larger. But all the lines across at this point, at this point we call it early voltage. Now, if we do mathematical representation, we found that this is the expression. Remember this one here is the inside circle is the current in the ideal case. So for any given VBE, we get a constant IC. It has nothing to do with VCE. For given IS and given VBE and VT, so you get IS. But in fact, for real BJT, you have to multiply by 1 plus VCE over VA. And then VA is called early resistance. As you can see, so now IC has something to do with VCE. Now VA is a constant. Okay. VA is like 5 volts, 10 volts. It's a voltage. So VCE over VA means it's like no unit. So it's a constant. It's just a value. And value 80 to 1 means IC is bigger. So as VCE increase, because VA is constant, you can see IC increase more, right? So what we said that is we call this a phenomenon of RO. So we say basically we try to okay. Let me do one more. So in this expression, if we do it, the front part doesn't change, so I just leave it, and inside it becomes VA over VA plus VCE. So inside the parenthesis is VA plus VCE over VA. And multiplied by, let's call this front part. Let's call it IC. So I further change this one to IC over, okay. So I just leave it like that. So it's like that. So what we're doing is we say that we use this one, we define. So this is a new variable we define, RO. It's called early resistance. And this is similar to what you can remember in the MOSFET. We also have definition RO. Yeah, so this is what definition we do. And from here, because VCE is small, VCE is small. So therefore, we got to this point. And what we are saying here is IC prime is this value here. This is what we get for the, like when we don't consider. So IC prime is when we don't consider the early effect. When we consider early effect, and then we have to, IC is IC prime times that variable inside. So what this gives you is a very interesting equation, is that the current of IC is no longer just this, and it has VA over IO over RO, and is added to the equivalent circuit. So from this expression, you can, from this figure, we can write like IC equal to IS e to the power VB over VT plus this let's call it VC E over RO. So the other term, the second term, is actually what we got from the previous page. If you go back to the previous slide, and you can see here is again the top equation over there. So there's two terms. One is IS VBOT, and the other one is VC over the whole thing. VC over VA, and then VA over this one here. VA over IC prime is RO. So that's why you got this one to be VC or RO. So this is our IC. And of course, this the equivalent circuit on the right hand is just basically converting that, instead of using IS times e to the power VB over VT, we just simply convert it to beta times IB. So in this case, your IC equal to beta times IB plus VC over RO. So these two are identical equations. It's simply changing the expression of between this is IB and IC. The other one is using VBE. Okay, so this is probably more used because more and more later we're not going to actually directly use this one anymore because this only in the initial phase that we correlate VBE, IS, and IC. Yeah, right.
Could you explain how we get from IC equaling IC prime 1 plus BCE over BA to that equation there?
Yeah, because here you see this IC has two terms, right? So if you look, we can rewrite this equation to the next one. So what? Hold on. So what it says that IC equal to IS e to the power VBE over VT, and then it's 1 plus VA over
VCE.
VCE over VA.
I just wanna see how that's connected to the one that you wrote.
right? So if you extend this term, this becomes is e to the power VBE over VT, and then plus another term is e to the power VBE over VT, and then times VCE over VA. Now, because what we're saying is RO equal to what we're saying is RO equal to VA over is e to the VBE over VT, right? So therefore, you can just simply plug in here. You can see, right? So it's is over E VBE over VT plus VCE, VCE over RO, right? So just replace that whole term because VA now it's on top, so it becomes RO.
Yeah.
So we got that. Now, if you basically saying, well, if you connect, so in the next couple of today's lecture and then next week too, we're going to start to give some names like common emitter, common base, common source, common collector, and so on. So the common here is just, I think, first time we introduced. Common means they're together. So common emitter means emitter is grounded. So common collector means collector is grounded. So what it says is that the source and the transistor has a common point, is the ground. So here, look at this diagram, little diagram over here. So what we're doing here in this diagram, we inject IB into the transistor, constant current source, and then we connect VCE to a variable voltage. In this case, when you change the VCE, the IC is going to change. So you basically can plot the relation between VCE and IBs, right? So what this is doing is like you fix IB, you're given like IB1, and you vary VCE. So you got like given IB, you vary VCE, you got this curve. You got one curve. Okay. And then you got IB2, and you do the same thing, you got another curve. So you got, when you do many different IBs, now you got a group of curves. You plot them together, you got the graph at the top. So that's what we call like a common emitter characteristics because the emitter is grounded. Okay, so later on we're going to see more of those common emitter. And what this tells you is that as IB increases, you can see that lines started to get slanted more. So if you, again, as we discussed before, if you extend the line down to the fourth quadrant or second quadrant, what is 1, 2, 3, 4? Yeah. So you're going to say, you're going to get that VA. So that's what really you get. And here, so that's look like, the more like a larger scale. But if you actually plot a little bit more detail, like in this graph, they just plot this like in a little bit more expanded scale. You can see here actually this area, this current goes like this, okay? And this slope over here, and it changes actually when you get close to zero, okay? But again, this area is not so much that we're interested. We're mostly interested, in this class is this area, and or in other classes you might be interested in the saturation operation and off and saturation. Okay, so but what this graph tells us is that when you want to operate this as an amplifier, you want to be in this middle region. You don't want to be too close to here because it might jump into saturation. Like even you say you just a little bit right about 0.3, even though you are in the linear region, but actually because just a little bit like change in the amplifier of input, you might actually run into the saturation region. So your system will become nonlinear. If you work in this region, actually, it might actually get too big, and it's close to your VCC's power supply. So therefore, you got another saturation at the upper end. So this is like a saturation low end. This is saturation upper end. So the ideally is we work in the middle region. Like if your VCE, let's say, in this case 0.8, you might want work at somewhere between 0.2 and 0.6. So maybe 0.5 is the ideal case. Okay. So if your VCE, let's say it's 10 volts, and you got a much, much larger range, and you can move up that operation, let's say close to 5 volts. So nothing special about this one. Just want to explain the relations of the BJT operation. Now, sometimes if the BJT is in saturation, so if the thing is in saturation, so from here to here is from base to emitter 0.7 volts, from collector to emitter 0.2 volts. And the current relation IC is no longer beta times IB. So this is critically important. So that's also what we're going to also many times. If you find that IC is no longer beta times IB, which means it is in saturation, that actual beta, we have a name called beta first, is IC over IB. So this is less than beta, and sometimes can be much less than beta. Like if beta is 100, beta first can be 50, can be 25, can be maybe even 1 or less than 1, depending on the relations. So we can have a simple example to look at the saturation mode operation. Let's say we have a BJT. Let's say we're going to inject IB to be 1 milliamps. I'm going to inject a very big current. So, and I'll tell you this already in saturation. So, now I tell you in saturation, of course, later on we can verify. So it's in saturation means VCE is going to be 0.2 volts. So IC is going to be 5 volts minus 0.2 divided by 1K. 4.8 milliamps. So now beta, I'm going to call it beta first because I know it's in saturation, is IC over IB equal to 4.8 divided by 1. It gives you 4.8. You can see here, it is quite in saturation because that beta first is much less than 100. So at this point, I want to ask you guys a question. So if I want to bring this thing out of saturation to make it in active mode, what are the things that you can do to make it happen?
have to. Decrease the current, either decrease the current of IC or increase the current of IB.
You don't decrease the IC, because if you decrease IC, better will be even smaller.
Oh, increase IC or decrease
Yeah,
IB.
you either increase IC or decrease IB, right? So if you decrease IB, for example, to 0.01 milliamps, now this beta is going to become like 480, which is, of course, it's no longer in saturation, so it will be active mode. So we have to recalculate what our VCE is going to be. VCE is no longer going to be 0.2. Now, you can also increase IC. Increase IC means you can decrease that resistance 1K. Right? So there are two ways to do that. Go ahead.
Could you explain again why in saturation mode VCE is stuck at 0.2? I always think of saturation mode as like a curve, and so I don't know, just maybe I'm missing something. Why is
Yeah.
it stuck at 0.2?
Well, in saturation mode, you mean going back to the physics, like why?
Is there like just a short explanation you could give me? Why is it why 0.2? Why VCE is at 0.2 instead of maybe there's an equation to calculate
Well,
what
we just defined it. That's just one of the things that we defined at 0.2.
Yeah, we did define that, but in fact, well,
I'm fine with that.
yeah, you will have to accept it, yes. But of course, there's physics behind it, because when it's in saturation means, there's p-n junction from base to emitter. That's in the forward region, but in the top region, actually it becomes, instead of a breaking down region, it becomes like a forward biased also. And then you get a 1 minus the other one, that gives you 0.2. You remember we have this diagram and it shows like you have lower it up to this point and it works that way. Yeah, probably I would say just accept it. Yeah. Okay. So now we're gonna go through an example. Okay, so this example asks us to determine the volume of VBB, so that A works in active mode with VCE to be 5 volts. Okay, that's like should be fairly straightforward. And B in edge of saturation. So what did it say? What it means in edge of saturation means it's right like between the linear mode and then the saturation mode, it's on the edge. So which means it's 0.3 volts. VCE 0.3. So what really that says is 0. So here, so VCE saturation edge is 0.3 volts. Okay, and C, deep in saturation means beta force is 10. That gives you, now, when it's in saturation, beta can be anything, less than beta. So the beta force, but here it asks you to design the circuit such that beta is first equal to 10. But of course, it did tell you that VCE saturation is 0.2 volts. Okay. So we're gonna solve the problem one by one. So VCE is 5 volts. So if VCE is 5 volts, we can easily calculate IC. So VCC minus VCE over RC, that gives you what? 10 minus 5 divided by 1 is equal to 5 milliamps. Yeah. I do this, you guys make sure I get the numbers correct. I did this already. Okay, so 5 volts, 5 milliamps. And then because it's the active region, so we know that IB is going to be IC divided by beta. And beta was given at 50. So 5 milliamps divided by 50, that gives you 0.1 milliamps.
Milliamp or 100 micron.
100 micron, yeah. So IB is given. Now, so VBB is what? Is IB times RB plus VBE, right? So that's a simple loop analysis. So VBB, I just want to point to the guys. So VBB is here, up there. So this voltage drop plus this voltage drop, and then this ground. Okay, so VBB over there. So it's fairly simple. So we get IB is 0.1 times RB is 10K plus VB is 0.7. That was given from previous slide. So we have 1.7 volts. So that's pretty straightforward. And then the second one asks you at edge of saturation. When it says at edge of saturation, it says VC equal to 0.3 volts. Now we can calculate IC is equal to 10 minus 0.3 divided by 1. That gives you 9.7. That's quite a big current. But since it's the edge of saturation, so the beta is still correct. So we can say IB equal to IC over beta. And beta is 50, so that gives you how much? 194. Yeah. So IB is given there. So now we say VBB is equal to IB times RB plus VBE. It's going to be 0.194 times 10 plus 0.7. That's plus 10 is 1.94. That gives you 2.64 volts. So the previous one we got was 1.7 volts. So now we got 2.64 volts as at edge of saturation. So you guys can imagine, as we go to saturation, this VBB needed is going to be more and more, right? Why? Because when VBB is small, IB increase. When IB increase, IC over IB becomes smaller. So that's what happens when it's in. So here, it's in deep in saturation, so VC is 0.2 volts. So therefore, we can calculate IC equal to 10 minus 0.2 divided by 1K, 9.8 milliamps. Now, IB at this point is given. So 9.8 divided by 10, 0.98. See, what's important is to use this beta first instead of beta because it's deep in saturation. So beta is given. Sometimes it's asking you to calculate beta force, but here beta force is given, so we calculate it. So, yeah.
On the first problem, could you explain again why VBE is equal to 0.7 instead of greater than 0.7?
Oh, VB was given at 0.7. Yeah.
Is the problem?
Yeah, VB was given.
Oh, there it is.
Okay, so now we can easily find VBB equal to like 10 times 0.98 plus 0.7. So that's what, 10.5 volts. You can see as you increase VBB, IB increase, and IC, of course, increase cannot catch that. So therefore, it enters a saturation mode. So that's this example. And okay, so now we're going to move into the BJT circuits at DC. Now, what really we're interested in this chapter, of course, we want to get all the different variations, different combinations of DC operation. And we'll be also talking about a little bit about biasing. But moving on to the next chapter, that's our focus is get the small signal model and get to how to do the biasing of the BJT circuit. So if you look at the DC circuit of BJT, we have two operation modes. One is in the active mode, and other one is in the saturation mode. The equivalent circuit for the active mode is that VB is 0.7, and VC is larger than 0.3, and IC is better times the IB. Okay, so this circuit is more like a DC operation that we use quite often in moving on in the future. Of course, for PNP, it changed a little bit. So E moves up there and B is here and C is there, but the relation doesn't change. So VEB is larger than 0.3 volts and VEB is 0.7. If it is in saturation, then we have VB also 0.7, but VCE is at 0.2. For the PNP, VEB is 0.7 and VEC is 0.2. This equivalent circuit are useful sometimes if you are not sure, what exactly you can do with the BJT symbol. But often you'll find that when we do problems, we don't actually go into the equivalent circuit. We basically direct analyze on the BJT symbol, which means this circuit is already written. We know that, okay, that's what we have. So you don't have to go into this circuit, to solve the problems. Now, just a little bit of clarification that in the saturation region, you see EBJ is forward biased and the CB junction is also forward biased. That's earlier you asked what happened. Because in the saturation, the C2B junction is now also forward biased. But in this case, the CB junction is reverse biased and it's actually in the breakdown mode in the operation in the active region. Yeah, go ahead.
I might be getting ahead of us
Yeah.
at this point, but how is this second in the saturation region? How is it affected by? This is just an ideal version. So when we have the saturated resistance model.
Oh, you mean so when you have the early voltage, early resistance,
Yeah.
it's going to be same here. Yeah. Yeah, it's going to be a resistor in parallel. Yeah. Yeah. And that the switching mode only, you guys only going to do that when you guys get into the 584, the power electronics. They use this sense as a switching device, which means it's either saturation or cut off. They don't want the linear region. Now, the reason they don't want linear region because, like example, if this thing is having a small current, like when you guys get into a 430, also you will look at power amplifiers. Like if this BJT or MOSFET, for the same reason, you have VCE is certain volts. Let's say your VCE is 5 volts, like in the previous example, and you got IC equal to like 1 milliamps. And then we have a power equal to V times I. So VCE times IC, that gives you 5 milliwatt, 5 milliwatts, right? So that's when we use this thing for a small signal, what you're doing, you're actually wasting 5 milliwatts on that transistor, right? Now, the 5 milliwatts of loss, most people wouldn't care. 5 milliwatts, it's very little. 5 milliwatts is like 5 over 1,000 watt. And 5 over 1,000, so 0.005 watts, right? And it divided by another 1,000, it becomes 0.000005 kilowatts. And 1 kilowatt times 1 hour is, say, 1 kilowatt hour is what you pay for your electricity. So that electricity can be like, I don't know, 1 over $1 million, right? So it's very small, so nobody really cares. But of course, it induces heat. If it's a single device, 5 milliwatts, nothing happens. But if you put 1 million of them together, you see what happens? 5 milliwatts times 1,000 give you 5 watts. Times another 1,000, 5 kilowatts. If you put 1 million together, 5 kilowatts, it's going to cook your meals, right?
Well, it's going to that.
Your your stove cooktop is about 3 kilowatts or 4 kilowatts. So a lot of heat. So that's why it's important to reduce the power loss. In power amplifiers, we want the VCE not too big. The current has to be small. If you want to reduce this to 1 volt, you reduce by 5 times. If you reduce the current from 1 milliamp to 1 microamp, see what happens? You reduce by 1,000 times. So all certain you reduce by 5,000 times. You do that, right? But unfortunately for BJT, it can't do that because the VB is 0.7. So that's where it comes back. Oh, why MOSFET? Because the MOSFET, the VGS can be as small as like 0.1 volt, 0.2 volt. That's the advantage. And also current. Biasing current for BJTs is always in the milliamps. So in ideal case, you can't put a million transistors together to make something because it's going to be too much heat. But MOSFET, you can do that because MOSFET operates in microamps. Okay, so what I wanted to talk is not this, but I was going to talk about the nonlinear operation. Now, if let's say VC is 5 volts and IC becomes, say, 100 amps, see what happens. You say, why 100 amps? Well, if you get a solar panel, and big solar panel, you want to convert the electricity to, say, an AC connect to your house, you need a lot of current. That could come to 100 amps. So if it's 100 amps, now your loss is going to be
500 watts.
Yeah, 5 volts times 100 amps gives you 500 watts. If you have 6 of them, that's 3 kilowatts. That's too much. So what do? You want to reduce. You want to use it in the saturation region. In the saturation region, it's 0.2 only. So in saturation region, its PC becomes like 0.2 times 100. That gives you what? 20 watts. Yeah, 20 watts is still big, but that's really manageable. Okay. Okay, so let's move on to another example. This circuit, a lot of the things were given, like VCC is given, RC is given, RE is given, VBB is given, and V is grounded. So we want to see, we want to find all the parameters. Then we want to know that the beta is 100 in active region. Now, first of all, this circuit is not in cutoff. Now, in this class, we always like make sure it's not in cutoff. But sometimes we will ask you whether it's in cutoff or not. But in this case, it's not in cutoff. Why? Because if it is in cutoff, you see IE will be 0. If IE is 0, then how much is that VE? 0. And your VBE becomes 4 volt. So that's not possible. VBE cannot be 4 volt. If VBE is 4 volt, in reality, your IC will be like 1,000 amps. It's too much. It's not going to happen, right? So VBE has to be 0.7 if either active or saturation operation mode. Okay, so now, however, we will not know whether it's active or whether it is in saturation. We don't know before we do all the calculations. So let's assume it's in active mode to start with. Assume it's in active, which means we can calculate IE. We know VBE 0.7, and we can calculate IE equal to VB minus 0.7 divided by 3.3K. So 4 minus 0.7 divided by 3, that gives you 1 milliamps. So IE is 1 milliamps, which means IC is going to be beta times IE, and beta is not beta, alpha. Of course, you guys know alpha is beta over beta plus 1. So that's going to be 0.99. So it's going to be 0.99 milliamps. So if IC is 0.99 milliamps, we can calculate VC. So VC is going to be 10 volts minus RC times IC. So 10 minus RC is 4.7 times IC is 0.99. That gives you how much? 5.3? Yeah, it's approximately 5.3 volts. Okay, so now we found VC and we know VE. Okay, we need to also find VE. V is 4 minus 0.7. That gives you 3.3 volts. So VCE now becomes VC minus VE equal to 5.3 minus 3.3. Okay, so at this point, we found VCE to be 2 volts, which is larger than the saturation voltage, which means it is in the active mode. So we're done with the problem. So it's fairly simple. But the last step, I'm going to find IB. You have 2 ways to find IB. You can find either IE minus IC, or you can use beta times IC, which is going to be 0.01 milliamps anyway.
Wait, I thought BCE was always 0.3. Yeah, so.
No, we see 0.3 when it's in the age of saturation. It's 0.2 when it's in saturation. When it's active, we don't know. It can be anything.
So BCE is 0.2.
We see is 3.3 with 2 volts here.
I thought you said it was 0.2.
The beta times IC does not make sense because beta is 100. So how is
But
100 times
you're smart.
times 0.99 1 million?
Sorry. No, this is in active mode, so we see is 2 volts. If it is in saturation, you will have VCE to 0.2 volts.
In active mode is
Anything more than 0.3.
it's anything?
It can be anything
Okay.
more than 0.3.
More than 0.
Yeah, we have to calculate it.
More than or peak.
0.3 is the age of saturation.
Yeah.
Yeah, we don't want to be on the edge. We want to be in the. Okay, so okay, I'll get a couple of slides. Let's do one more problem, then we're gonna stop. 6.5. All right, so in this problem, we want to determine all the voltages, currents through branches. Now this circuit is identical to that simple, except the voltage base is now 6 volts. Assume beta is 50. So again, this will not be cut off because everything is cut off. VE will be 6 volts. That's not possible. So it's going to be either active or in saturation. We assume inactive. So therefore, VE equal to 6 volts minus 0.7. So VBE equal to 0.7 volts, 5.3 volts. Yeah. So that's step 1, step 2. And step 3 is to find IE equal to VE over RE, 5.3 divided 3.3. That we need to give actual value is going to be how much? I didn't calculate. How many milliamps? Okay, I need to get some sort of value. It's 1 point something. Can you some people calculate? Well, what I can do is I can go to IC equal to alpha times IE, I get another value.
6.1.
What is 1.61, okay. Can we calculate IC? It's probably 1.6, I would guess, or 1.59. So now we calculate VC is 10 minus RC times IC. It's going to be 10 minus IC. How much is IC? 1.5, 1.59 times 4.7. You calculate how much this one is? 2.5.
Like, 8.
So VCE is now going to be VC minus VE, and VC is 2.5 minus 5.3. That gives you negative 2.8 volts. You see what happens now? VCE becomes negative. We always said, no, that's not going to happen. VC cannot be less than VE if it's in operation, whatever operation. VC cannot be running lower. Like, look at the circuit, right? How can you get VC lower than VE? It's impossible. VC has to be larger than VE, which means our assumption is wrong. So it's wrong. Yeah, we have to start to look at it in saturation mode. Let's see, do I have a slide? Yeah. So the next one will be, we assume in saturation. So I'm gonna just do it here. Assume in saturation. So if we assume in saturation, we see it will be 0.2 volts. So now, remember, this VBE is 0.7. So IE doesn't change. So IE is going to be, it's going to be 6 minus 0.7 divided by RE is 3.3. So that doesn't change. That was 1.61. So what it changed is, step 2 is VC now is VE plus VCE. So VE is 5.3 volts plus VC is 0.2. That gives you 5.5 volts. So that's VC. And then, yeah. So in the diagram here, it says number 3. So that's number 3. Step number 3. Yeah. So, and then we're going to go to step number 4. We're going to calculate IC. So IC is going to be VCC minus VC. So it's going to be VCC minus VC over RC. And VCC is 10 minus VC is 5.5 divided by 4.7. That gives you 4.5 over 4.7, 0.98, some millions. 0.96.
Clearly also there.
Yeah, it's just a little error. Okay, so IC is 0.97. So now we can calculate this better first. It's IC over IB. Of course, before that, we have to calculate IB, which, let's see, let's do 5 over here. So 5 is IB equal to IE minus IC. So IE is
1.6.
1.61 minus IC is 0.96, right? So 0.65. Yeah. So IC is 0.96 divided by 0.65. That gives you a very small number, 1.5. You see, that beta first is very small, so it is in saturation mode. So that's what I'm mentioning earlier, saying, well, you can assume one mode, but you have to verify. If you forgot to verify, like in the previous step, like we could go well, it's actually on this side. If you don't verify the last step, you just say, oh, okay, I got VB is 5.3, and I got a VB is 2.5, and you say, oh, everything looks good. You're wrong because you forgot to verify VCE has to be larger than 0.3. In active mode. Well, it is if it is in active mode, that's the beta. But when it moves into saturation, it's no longer true. No. So assume beta is 50 for active mode. That's how we did it in the previous. Yeah, I mean yeah.
But in this problem, it's super. We don't actually need to know.
You don't need a beta, right? Exactly.
I thought we assumed it was 100.
Huh?
It wasn't 100 we assumed.
It doesn't matter. It doesn't matter. It says beta 50.
Oh, yeah.
Beta 50. But you don't need, you don't, I mean,
At 50, but it's
if it is active, we would need this.
Yes.
But since it's not inactive, this number doesn't help anything. Yeah. Okay, any other questions? If not, then we're gonna stop here because there's not enough time to go to another problem. Yeah, so we have 2 more lectures on this chapter, then we're gonna go to our final, second middle term on November 6th. Time flies, I know.
So what's that one going to cover?
MOSFET and BJTs. 2 more lectures before.
So next Wednesday, we're going to have our.
Middle term is, I believe it's on Thursday next week.
Oh, yeah, Thursday.
Yeah, so we have Thursday this week and Tuesday next week. So it flies, I know.